Hello everybody. In this video I want to give you guys all the things that you're going to need to be successful in the freezing point depression lab and lab flow, and give you a little introduction to what we're going to be doing with the report. So freezing point depression is one of the colligative properties. And colligative properties are properties of solutions that only depend on the concentration of the solute or solutes and not the identity of the solute or solutes. Some of the colligative properties include boiling point elevation and the closely related vapor pressure lowering. There's the one that we're going to be talking about today in our lab, freezing point depression, sometimes also called melting point depression, because, if a liquid goes to a solid, it's freezing, but if a solid goes to a liquid, it's melting. It's really the same thing. It's just a directional kind of thing. And then, as we've already talked about, the osmotic pressure. So freezing point depression is governed by this equation here, where we have delta T, which is equal to this T star minus the temperature of the solution, so the change in temperature, and that's going to equal Kf times the molality times this I factor. Delta T is the difference between the temperature at which the pure solvent freezes, so solvent without solute is T star, and the temperature at which a solution made with the solvent freezes. So once I add solute and I made a solution, I have a different temperature that it freezes here, T-sol. And because it's freezing point depression, T-sol is always going to be less than the pure T-star. And that means that delta T is always going to be a positive value. Kf is the Molar freezing point depression constant. And this constant is specific to the solvent. So depending on the identity of the solvent, it's going to be more or less sensitive to having solutes added to it and changing its freezing temperature. And Kf reflects that. So when Kf is large, then the addition of solute is going to cause it to have quite a bit of freezing point depression. When Kf is small, then even adding quite a bit of solute isn't going to change the temperature at which it freezes very much. M is the molality of the solution. And as we learned before, molality is equal to the moles of solute divided by the kilograms of solvent. I is something called the Van't Hoff factor. It is equal to the number of ions per formula units that are formed when the solute dissolves. So in the case of, say, like if you have methanol liquid and you add it to water, you still have one thing here. This guy doesn't really ionize or break apart, so I equals 1. In the case of sodium chloride going into water, it forms these two ions, so I equals 2. If you had something else that broke up into, say, 3 different ions, I would equal 3. In our lab, though, we're going to just assume that I is 1. We're using only organic solutes and solvents, and they're not going to ionize. We don't have an ionizing solution, so I is always going to be 1 for us. We've taken a look at something like this before when we were talking about energy and temperature and phase changes, and we said that what we're going to have here is if I'm measuring the temperature as something is steadily cooling, so the same amount of heat is being removed throughout this time here, then I can use time on this axis. I'm first going to have a liquid in this whole region right here. Eventually, it's going to plateau out. At this point, solid and liquid are forming and exist in an equilibrium. And then eventually I'm going to get all solid, and then that solid is going to continue to cool down. This temperature right here that corresponds to this plateau, if I traced it back over here, this is going to be our freezing point. In practice, however, our data usually doesn't look that great. And what we wind up with is often something that kind of looks a bit like a little bit of a curve here. It's not a perfect straight line. Then there's like some sort of inflection point, and then we get a different slope as we go out. We don't really get that full plateauing. Instead, it just kind of changes slope before and after, because the rate at which the liquid would be cooling is different than the rate at which the solid would be cooling. Here we have the inflection point where they join, and if I trace that over, that's going to be our freezing temperature. Now, if we did this slowly and carefully enough, we would get this, but that's often just a little too difficult to reproduce in the lab. And what we have to do is we have to figure out what this point is. And typically what we're going to do is we're going to have a line, like a linear regression, that's going to be represented by this section here, and we're going to get an equation for that, y equals mx plus b. And then over here, we're going to have a different line that's going to line up with that and come out here, and that's going to have its own equation, y equals mx plus b. So we have our two different lines, one representing this bit of data and the other one representing this bit of data here. Now we need to figure out where two lines intersect, and that's just a bit of algebra. What we do is we set them equal to each other. So I'm going to have m1x plus b1 is equal to m2x plus b2 here. And I'm going to solve for x. And when I do that, I get b2 minus b1, m1 minus m2 here. And what this value is it's this point right down here on the t-axis. So it's the time when it started to freeze. And if I want to know why, this point right here, I'm going to take the x value that I calculated and I'm going to plug it into either one of these equations. So I chose to plug it into this one. I just took the output of what was x and I plugged it into that equation to give me an equation that's going to tell me the temperature at which it froze. We're going to be using Excel to do this, and I'm going to upload a video under the report section to kind of walk you through it a little bit.